Welcome to my session. And so we continue with the Volterra problems. And I have brought few more problems for you just for practice. So we solve example 3. It would be, okay, this is part 2 of my previous video. Okay. Let's solve. So you have y of x equals x plus integral 0 to x sine of x minus t and then y of t dt. Okay. We want to find out what will be my y of x. Okay. What will be my y of x? Let's solve. Okay. So in the same problem you have here, the first thing that ultimately should come into your mind is to differentiate this same problem. Okay. Otherwise, I'll tell you one more method. See, because I see that this kernel here is of this type. Okay. Kxt is of this type, f of x minus t. So this is a convolution type kernel. Okay. Once I understand the Laplace transform, I can think of applying the Laplace transform to solve this problem. So I'll even explain this, okay, how to solve using Laplace transform. Okay, stay with me, but first let me begin with Newton-Lenn's method. So I'll differentiate this. So I'll be getting y dash x equals 1 plus integral 0 to x and then partial derivative with respect to x of sine of x minus t and y of t dt plus this entire quantity will be here sine x minus t and y of t. This goes for t equal to x and its derivative and then minus the same quantity sine x minus t and then y of t at t equal to 0 and its derivative will be 0. Okay. Now I'll be getting y dash x will be equal to 1 plus integral 0 to x. This integration of sine, derivative, partial derivative of sine with respect to x will give me cos x minus t and then y of t dt. Okay. Plus at the place of t, if I substitute, I'll be getting here, this quantity will be getting completely 0. Okay. This quantity will be 0 right here. Sine x minus 0 will be 0 and then y of x will be there, but because of this quantity it will be 0 and again this quantity will be 0, right? Now here I have to differentiate one more time because I cannot make any substitution because I have got here cos. So ultimate thing would be to differentiate once again. So y double dash x will be, this one will go this time, and then integral 0 to x. Now I'm not writing this sign, I'm directly differentiating with respect to x. So derivative of cosine will be minus of sine x minus t into y of t dt and then plus this cosine will come into the picture, cos x minus t then y of t. This works at t equal to x and then here its derivative is 1 and then minus cos of x minus t then y of t. Derivative is at t equals to 0 and then its derivative 0. All right. Now this quantity will give me y double dash x will be equal to minus of this integral, okay, right here will be 0 to x and then sine of x minus t y of t dt. Now if I put here t equal to x, this quantity will give me cos 0, that is 1, and then y of x. So I'm just getting here y of x. And now if you look at the question very carefully, then you see that y of x minus this quantity. So if I have here y of x, if I take this quantity to the left hand side, so I'll be just having x. So instead of this big quantity, I can just write down y double dash x will be equal to simply x. Okay. And for this I have to write down the reason that y of x minus, I'm rewriting the equation one again. So sine x minus t, then y of t dt, this will be equal to simply y of x minus this quantity that will give me just x. Okay, so I got y double dash x equal to x. All I need to do is just integrate it twice. So when I have y double dash x equal to x, I'll be now finding y dash x Okay, so it will be integrated. So x square by 2 plus some c1, some constant, and again when different integrating once again, so I'll be getting here x cube upon 3 into 2 plus c1x plus some c2. And now anyhow I have to remove these two constants c1 and c2. So to remove or to find, okay, to remove constants, we impose initial or boundary conditions. Okay, so we impose conditions. Okay. Since this is Volterra here, okay, so I'll not be having boundary conditions, it will be initial. So let us go. If I say y of 0, then y of 0, it is clear, it's 0 plus integral 0 to 0, this entire quantity, this will be 0. So I can say from this quantity, okay, I can say if I put here y of 0, I'm getting here 0 plus integral 0 to 0. No matter what this quantity is going to be 0. So I got one condition from this side, okay, that y of x equal to this quantity, and then I have y of 0 equals 0. So I have one condition, y of 0 equal to 0. So I'll say since y of 0 equal to 0, that's one condition, and I need to find out one more condition because I have two constants. So I'll impose another condition on the its derivative part. So let's go. I have y dash x here. So if I put 0, okay, the same quantity that I had told you. If I put again y dash 0, then I'm getting here 1 plus integral 0 to 0. So this quantity right here will go and meet 0. So I'll be just having y dash 0 equals 1. Okay. So in that case, I'm having y dash of 0 equals 1. Okay. Now let's impose. So since I have y of 0 equal to 0, so if I substitute this quantity here, so this will give me 0 equals 0 plus 0 plus c2. So this implies c2 will be 0. So in that case, c2 will be 0. So in that case, c2 will be 0. And now if I impose another one, y dash 0, then I'll be getting 1 equal to 0 plus c1. So in that case, c1 will be equal to just 1. Now let us substitute here. So y of x will be equal to x cube upon this here will be 6 and c1 is x. So I have this quantity. All right, this is my y of x. Okay. So you must have got the flavor how to solve such kind of problems. It's all about differentiation, nothing else. Okay. There are a few more methods like resolving kernel that will be done in the next part. So in this part, I'll be just doing some problems based on Volterra and Fredholm both. So this completes one problem. And now if you want, it's another approach by using Laplace transform. So let me apply Laplace even and prove that this solving the same equation by Laplace transform is quite easier than differentiating this whole thing. Okay. So let me solve by Laplace transform. Okay. So let's say we have another approach. That's by Laplace transform. And for those who are new to Laplace transform, you can watch my upcoming video based on Laplace transform, okay, so that you can get a good practice and then come back here. Otherwise, I have given you already one approach you can apply, and I'm sure you will find Laplace transform easier. As if you are not getting it now, but if you already have studied Laplace transform somewhere, then you would find this part quite interesting and easy as compared to the previous one. Okay. So let me apply the Laplace transform, and I'll see a Laplace transform can be applied to Volterra equations. Okay, let me mention it here. This you can apply here to f of x plus integral some a to x. Okay, and then your kernel must be of this type. Okay, some f of x minus t type. Okay, convolution type kernel. Okay, and then y of t dt. Then I can apply Laplace transform. And if I apply Laplace transform, I'll be denoting this L of y of x by y bar. So also I'll be getting here y bar equals to Laplace transform of f of x. Okay. Plus if I take the Laplace transform this quantity, then it will be just, okay, it will be just a Laplace transform of this entire quantity f of x minus t again. Okay, and when I'm taking the Laplace transform, then f of x minus t will get dissolved into something. Okay, and ultimately you have to take the Laplace transform of f of x only. Okay, no matter whether you have x or t. Okay, and then apply just y bar. Okay, that's it. This is again Laplace transform of y of t. It is called convolution type kernel. Okay, and if you are completely new to it, then do not worry. I'll be preparing separate video for this. Okay, in which I'll discuss how this entire quantity is coming. But for the time, just you can keep this thing. See, even if you have the Laplace transform f of x minus t, you have to take the Laplace transform with of x only. Okay, so let me solve the same problem by using Laplace method. Before that, let me rewrite the problem. What I had, y of x equal to x plus, yeah, fine. So you have y of x equal to x plus integral 0 to x sine of x minus t into y of t dt. Okay, and the another best part of the Laplace transform is that you don't have to apply your boundary conditions or initial conditions. You don't have to worry about it. Let's see. Okay, so I'm saying taking Laplace transform of given integral equation. So I'll be getting, I'm writing this y bar. Okay, when I'm writing y bar, that means I have already taken the Laplace transform y bar. Okay, now I want Laplace transform of x. Okay, so Laplace transform of x, here power is 1, so it will be basically gamma 2, okay, upon s power 2. Okay, this is the Laplace transform formula. I'll mention it, and plus this Laplace transform of, you can even mention it or you can simply take it. So for your simplicity, I'll write down Laplace transform of sine of x into, just write down y bar. Okay, see, for those who are getting confused, that Laplace transform, it actually takes from time domain to frequency domain. So you have here L of f of t, so you get something into phi of s. Okay, so instead of t, I'm replacing by the variable x, so this does not make any difference. Okay, still you get a function of s only. Okay, so now let me mention the formula which converted this. So I know that Laplace transform of t power n is nothing but gamma n plus 1 upon s power n plus 1. This gamma n plus 1 is nothing but n factorial when n belong to set of integers. Okay, that plus. Okay, because gamma of negative integers does not exist. Okay, so let's solve. Oh, I'm sorry, I'll keep this formula intact. Yeah, now I'll take the Laplace transform of sine even. So let me write down the Laplace transform of sine x. Okay, so it will be, see, basically we deal with the Laplace transform of sine ax. So here a is 1. Okay, so in fact I'll mention it more precisely by doing this, sine of ax. Okay, so it is a upon s square plus a square. This is the Laplace transform of sine ax. So here a is 1, so I'll be getting just 1 upon 1 plus s square. So let's write down. So this will be y bar equal to gamma 2 is nothing but just 1 upon, this is s square plus Laplace transform of sine x is 1 upon s square plus 1 y bar. Okay, now your task here would be to collect all y bars together and take its inverse Laplace transform, and remaining part would be your solution. Okay, so let's go. Now I'll collect these two terms together because I see their y bar. So it will be y1 minus 1 upon 1 plus s square times y bar will be equal to 1 upon s square. Okay, so in that case, I'll be getting 1 plus s square minus 1 upon 1 plus s square. So this 1 and this 1 will be getting cancelled, and I have here y bar equal to 1 upon s square. Okay. Now let me utilize the next page. So s square upon 1 plus s square y bar equal to 1 upon s square. Okay. Now for the simplicity, just make sure we are correct. Yeah, s square and then 1 upon s square and then s square. Yeah, that's correct. So now our job would be to do this. Y bar will be equal to 1 upon s power 4, and this quantity will come here, 1 plus s square. So y bar equal to 1 upon s power 4 plus this one will be 1 upon s square. Okay, so now taking inverse Laplace transform. Inverse Laplace transform. So if you can go from here, that is L of f of t equal to phi of s, then you can again gain your f of t by taking its Laplace inverse. Okay, so if you remember, then we had done this. L of x square, we had written 1 upon s square in this step. Just check this. Oh, it was x, I'm sorry. Okay. L of x was 1 upon s square. So if I take inverse Laplace, okay, so I gain this L inverse of 1 by s square will be s x. So now let me write down the general formula so that you don't have to remember each and every time. Okay. So the general formula for this is L inverse of, okay, let me write down the general formula. Yeah, L inverse of 1 upon s power n will be equal to t power n minus 1 upon gamma n minus 1. Okay. No, I think there is one correction here. Yeah, it's not t power n minus 1, so it will not be gamma n minus 1. It should be just n. Okay, it is gamma n. Okay. Because gamma n, if you expand, you will ultimately get n minus 1 factorial. So that is what I mean to say. But here I wrote by mistake n minus 1. Now let's go. So if you apply this formula, then you are getting here. See, when I'm taking a Laplace, inverse Laplace, I'm just getting here y of. And remember, with respect to what you had taken the Laplace transform. So in case you have here, you have taken with respect to x, then please do not write here y of t. Okay, please do not write y of t, because sometimes what they do is they ask you certain conditions like y of something. So in that case, you may get confused like it is t or x. Okay, so it will be y of x because we want solution in x. Why x? Because here it's an unknown function of x. That's why. So y of x will be equal to, now take its inverse Laplace. So that will give you t power 4 minus 1 is, oh, I'm sorry, not t, x. Okay. It will be x power 4 minus 1 is 3. Compare this quantity with this 1 upon s power n. So you get x power 3 upon, okay. So it will be gamma. I think I was correct. Gamma n minus 1. Okay. So that will be gamma n minus 1 will be gamma 3. Why I'm writing this gamma 3? It's gamma 4. Yeah, because it is n. So gamma 4 will be 3 factorial. Okay, plus 1 upon s square. You already know this is x. Now if you open it further, you get y of x equal to x cube upon gamma 4 is nothing but 3 factorial. Okay, plus x. You got the same solution. At one step, it may look confusing, but it is not so if you practice a lot many problems based on this inverse Laplace transform and Laplace transform. When you have a convolution type kernel and you got a Volterra problem, so you can simply apply this method and solve the problem. All right. Now let's solve one more. So this problem is coming from CSIR-NET June 2017, and they had given let phi of x be the solution of this quantity 0 to x e power x minus t into phi of t dt equals x. Then they need the value of phi of 1. Okay, quite easy to solve. Now, one method is always there for you to differentiate it. Okay, to differentiate and get the answer. So that's the most obvious one. But here we will apply Laplace. Okay, we will apply Laplace transform. Or you want just let me do both the methods. Okay, just for your simplicity. So first thing, I'll differentiate it. So if I'm differentiating, I'm getting 0 to x. Derivative of this quantity will be the same thing again, because I have here e power x minus t, and then plus e power x minus t, and then phi of t. Derivative will be at t equal to x, and derivative of x is 1. And if I put this quantity, then this will not contribute anything, so I'm not writing, and derivative of x is 1. Now I can replace this quantity by x. So it will be simply x plus, now here I'm getting x minus x will be 0, so e power 0 will be 1. Here it will be just phi of x will be equal to, here it is 1. Okay. So phi of x will be equal to 1 minus x. So they want value at phi of 1. So phi of 1 will be equal to 1 minus 1 will be 0. Okay. So B option is correct. Just by writing 2 steps, you got 3 marks. Okay. This question was for 3 marks. And now, if you try to approach, if you try Laplace transform approach, then let's do even that one. 0 to x e power x minus t into phi of t dt will be equal to x. All right. I think this was the same problem. Yeah, right. So let's go. Take the Laplace transform. So you get here L of just e power x, okay, into, I'm writing here phi bar. Okay. It will be equal to Laplace transform of x. Last time we had seen it was just 1 upon s square. Now take the derivative of, Laplace transform of e power x. So let me mention here the formula for L of e power a. It was t, but here I'll write down in terms of x. So it is nothing but 1 upon s minus a. Okay, 1 upon s minus a. Here my a is 1, so I'm getting Laplace of e power x will be equal to just 1 upon s minus 1. So replace here. So you're getting here 1 upon s minus 1 into phi bar will be equal to 1 upon s square. So phi bar would be s minus 1 upon s square. Okay, so phi bar would be equal to 1 upon s minus 1 upon s square. Okay. So if I simply see this quantity, then 1 upon s square, you know that already it is just x, and 1 upon s. 1 upon s can be taken from here. What happens if I put a to be 0? Okay. For a equal to 0, I know that Laplace of e power 0 will be equal to 1 upon s. So e power 0 is 1. If I take the Laplace inverse, then it is 1 upon s. So this is nothing but 1 minus this is nothing but x. So you got phi of x equal to 1 minus x. Again, if you apply, then phi of 1 will be equal to 0. So I want to solve the same problem using Laplace. Okay. Here you don't have to worry about anything if you know Laplace transform. All right. Now let's take few Fredholm problems, and then I'll give you another method how to convert differential equations into Fredholm problem, its corresponding, and vice versa. And there will be a iterated kernel method, and at the last it will be an introduction of eigenvalue problems here to find characteristics number. Okay, how many solutions any equation can have. Such kind of things will be included in part 4 and part 5. Okay. So let's go to solve some Fredholm problems. So let's solve this Fredholm integral equation. Okay, they're asking which of the following is a solution of Fredholm integral equation y of x equals x plus. Now, since the limits are constant from 0 to 1, so we can easily say that this is going to be a Fredholm, not going to, it's Fredholm integral equation basically. And now we will solve by separable kernel method. Okay, because here I see that x and t are separate, so I can apply the method of separable kernel. So what is method of separable kernel? Just say this: y of x is nothing but x plus, see, this integration is totally with respect to t, so there is no role of x. I can take this x outside, and then it will be completely a function of t. Now I know that since this is a definite integral, so this is ultimately going to be a constant. Okay, this is ultimately going to be a constant. So what I'll do, I'll take let integral 0 to 1 t into y of t dt equal to some c, a constant. Now substitute here again. So this implies your y of x becomes x plus cx. Okay, because this quantity right here is c and then x. So y of x is nothing but x plus cx. This is what we have. And now let's get back. So my c was nothing but integral 0 to 1 t into y of t dt. So c equals integral 0 to 1. This is t. What is my y of t? So y of t is this. Okay, here at the place of x, if you write down just t, you get your y of t. It will be t plus ct. Okay, so t plus ct dt. So c will be equal to integral 0 to 1. This is t square dt plus c, then integral 0 to 1 t square dt. Okay. Or for simplicity, what I can do is I can take even this quantity common and take 1 plus c. But now since we have exceeded one step, so it's better to integrate it. So I'll be getting here 1 by 3 if you integrate. And here also you get here c t squared. It will be again 1 by 3. Okay. So if I take this quantity here, so 3 minus 1 will be 2c by 3. Okay, equal to 1. So this implies c will be equal to 3.2. So once you got c equal to 3 by 2, simply substitute here, okay, in equation 1. So your y of x was x plus cx. So you got c to be 3 by 2. So x plus 3 by 2x. Okay, that is my solution. But again, one moment. I think there is some problem here. Okay, there is some problem. What mistake we did? Because I don't think so. Any option is matching with this one. 3 by 2x is fine, but why this extra x is coming from? We need to check where we went wrong. Y of x equals x plus. Okay, fine. So x times. So I took this t out. And then 0 to 1 t, and then y of t dt equals some c. So y of x equal to x plus cx. This is again fine. Y of x was t plus ct. Yeah, right. And so t times y of t dt. Oh, okay. Yeah. Here we made a mistake while solving. It was 1 upon 3. Okay. It was 1 upon 3. Okay. So this 3 and 3 will get cancelled. C will be half. Okay. Not 3 by 2. C will be half. This is where we went wrong. C. Okay. After this step, let me write down. C minus C by 3 will be equal to 1 by 3. Okay. So you get here 2C by 3 equals 1 by 3. So C will be half. If I put C equal to half, then my equation now gets reduced to 1 by 2. So y of x will be basically 2 to 1 plus 3. Yeah, 3x by 2. Okay, so that's my solution. 3x by 2. B option. And suppose in the case you're not able to think about anything, and if you look at the options very carefully, then there is x everywhere. Okay, that means if I can just find out this constant, then I'm done. Okay, I'm saying just another cheat approach. Okay, how you can easily think about the solution even if you have not studied integral equation or anything. you know that this is going to, your solution is going to satisfy this integral equation. So what I'll do, I'll assume that solution is given by, okay, or assume the solution is given by y of x equal to some constant times x. Okay, because I see that solution is given by, see, this is a constant cx. So I can easily say that its solution is going to be cx. So if I can find out this c, I'm done. Okay, so let's substitute this y of x into this quantity. So my equation is y of x equal to x plus integral 0 to 1 x into t to y of t dt. Fine, now I'll substitute the cx. So I'll be getting cx will be equal to x plus integral 0 to 1 x. Okay, this will be t, and then y of t is again ct dt. Okay, so cx will be equal to x here, and take this x out. So you get integral 0 to 1. Even you can take c out. So it will be t square dt. And now cx will be equal to x plus, this is again cx. If you integrate, you get cx by 3. Okay. Now just check this quantity here. So I see is x cutting, in fact, x is getting cancelled. Okay, so first, in fact, let's take these two quantities together. So I'm taking cx minus cx by 3 will be equal to x. So x is getting cancelled, and I'll have 3c minus c. So 2c by 3 equal to 1. So this implies c will be equal to 3 by 2. Now you can easily just plug in here. Okay. So y of x equal to 3 by 2x is your solution. This is another approach. So you are sitting in the exam, CSIR-NET. If you cannot think of some method, okay, try to cool down yourself and think of something which you already know. Okay. So rest of the part, this Fredholm integral equation, and its another part will be considered in the next session. Thank you so much for watching. See you.